over the last couple of weeks, we've been working on one of our modules, which was random processes, random numbers, Monte Carlo methods, and we looked at a number of sort of classic examples of those topics: radioactive decay, Brownian motion, macroscopic properties, solids, gases. So today's class, we're going to move on to, and for the next few classes, move on to least squares fits. And we're going to kind of start in the simplest way with the simplest fit, which is basically a least squares fit to a straight line. And in this case, we're going to consider the uncertainties on the data points that we fit the straight line to. We'll consider those uncertainties as common to every point. It's the same for every point. And then over the next few classes, we'll make the fit more sophisticated. We'll look at fits beyond just a straight line to a more general curve. We'll look at fits where we incorporate the individual uncertainties on individual data points. And we'll also move from fitting using our sort of homebrewed code for the least squares fit, which is good for a straight line, to using library codes, which is much better for general curve fitting. So, as I say, in today's class, I'm just going to focus on a fit to a straight line with equal uncertainties. The couple of examples that I've got of fits to straight lines, you might think there's not many interesting examples of fits to straight lines, but there are some sort of classic examples of fits to straight lines. One is the expansion of the universe. So the conclusion of the expansion in the universe and the parameters of the expansion of the universe come out of a fit to a straight line. And then the other one we'll look at is, and is a part of the assignment, is Kepler's third law. So Kepler's third law is a relationship between the period and the radius of planetary orbits. And we can analyze that through a straight line fit, and we can determine the mass of the sun through that straight line fit. So there are quite interesting and important, significant straight line fits. Oh, I didn't mean to do that. Okay, so first few slides here, I just got an introduction to the expanding universe as a sort of classic example of a straight line fit. And then I've got a few slides on how to sort of mathematically solve a straight line fit to some data points. And then I've got a few slides, and we'll look at my code, which correspond to sort of computer implementation or Python implementation of a straight line fit. Anyway, so of course we all know Erwin Hubble and his discoveries. Two of the key discoveries were made with a type of star, which is a very bright variable star, where there's a kind of a known fixed relationship between the brightness of the star and the periodicity, the variability of the star. And so these types of stars could be used as kind of standard candles, in that knowing how bright you observe them to be, you can determine the distance of those stars from us, from Earth. And so Hubble used that for a couple of important discoveries. This first one here, I just mentioned it, is that by looking at these stars, he concluded the existence of more than just our galaxy, that there are other galaxies beyond the Milky Way galaxy. And that was from observing these very bright variable stars as standard candles. And the second famous conclusion was related to the expansion of the universe. So if you examine these stars in different galaxies, you can you can determine the distance to the galaxies based on the brightness of these stars, and you can determine the velocity of those galaxies relative to us, Earth, based on the shift, the Doppler shift of spectral lines from these stars. And so you can study the relationship between the distance of a galaxy from Earth, from us, and the velocity of that galaxy away or towards us. And Hubble plotted this data. He made a straight line fit to this data. And this data basically showed you, I put the conclusion here, that the greater the distance the galaxy is from Earth, then the greater the speed that it's receding from Earth. So the recession speed of the galaxy is in proportional to the radial distance to the galaxy, and the conclusion you draw from that is that it's not that Earth is somehow special in the center of the universe. It's that everything is receding from everything else in the universe, that the space and time of the universe are expanding. And so that was a huge discovery, obviously, based on a straight line fit. Hubble's discovery, as I say, was kind of first evidence for the expanding universe, and Hubble's discovery supported the Big Bang hypothesis of the creation of the universe. The law is, Hubble's law is also often written in this little fashion here. So in this little linear equation here, d is the distance to the galaxy, v is the recession speed of the galaxy, so they're proportional to one another, and the proportionality constant is the uppercase h here, the Hubble constant. And so that's measured, that's determined by making a plot of the recession velocities versus the galaxy distances, and fitting a straight line to that plot. The straight line intersects with the origin, and the slope tells you the Hubble constant. So the Hubble constant, if you extract it from the straight line fit, is 70 kilometers per second. That's units of recession velocity divided by megaparsec. So that's units of distance to the galaxies. The closest distance to a galaxy is sort of about 1 parsec, I think. So just to give you a scale. But if you had a galaxy that was a megaparsec away, so 1 million parsecs away, then it would be receding from us at 70,000 kilometers a second. I'm wondering if I got a missing factor in here, actually. I better check that. Anyway, if you take the reciprocal of the Hubble constant, that's a time, that's a Hubble time. You can see it from the units there. You've got units of speed over units of distance. So that's inverse time. And so the inverse of the Hubble constant is a time, and it's basically the age of the expanding universe. It's the age of the expanding universe under this assumption, right, that that expansion isn't accelerating or decelerating. So if it's just this sort of constant expansion. For a long time, it was thought that, well, it would probably be slowing down. The expansion would be slowing down because the universe is filled with matter, and matter is gravitationally attracting each other, so slow the expansion down. Nowadays, it's been observed that the expansion is speeding up, and the presumption, the explanation is due to dark energy, which creates the expansion of space and time. Okay, so that was just a bit of background physics to motivate fitting to a straight line can be quite interesting and can be quite important. Um, sorry for that story. Um, anyway, this is a fit to a straight line. This is the fit to Hubble's flow or law. Um, in this particular plot, I've actually got the on the horizontal axis a proxy for the velocity of the galaxies. So it's actually the fractional redshift of the galaxies. The faster the galaxies are traveling away from us, receding from us, the greater the redshift. And so this is the fractional redshift, the proxy for the recession velocity. And then it's plotted vertically versus the distance to the galaxy, the radial distance to the galaxy. And you see in magenta here are individual measurements using individual bright variable stars that are standard candles, and in green is the fit to the data. And so this is how you extract the Hubble constant or the Hubble time that are written down here. The age of the universe, 15 billion years. So that's a nice example of a straight line fit.